Hello, in this video we'll be talking about symmetry and symmetry operations in molecules. Symmetry in molecules, not just symmetry generally. My name is Dr. Wino. This is a part of a video for Department of Chemistry, University of Lagos. Okay, symmetry, let's look at it. Symmetry is a property of an object. Any object, even a human being, has some symmetric lines. Is a property of an object by which the pattern of the object can be brought from its initial position to another, still the same object, another indistinguishable position, which means it looks exactly like it was before, like nothing has been done to it, by means of certain operation known as symmetry operations. For example, this square shape, if we flip it along this line, it still looks like the square shape. So if it's supposed to fit into a key, it will still fit into the key. A lock, if it's like a key that fits into a lock. So this, if you flip it along this line, it still has that symmetry. The rectangle, so the 4 lines of symmetry on the square. The rectangle, if you flip it horizontally, you still have the shape of the original rectangle. If you flip it vertically, if you flip, you have the shape. If you flip it diagonally, it doesn't give you that shape. So the kite also has a line of symmetry. The isosceles trapezoid has a line of symmetry, but the regular trapezoid does not have a line of symmetry. There's no way you will flip it and get it to the original, to the indistinguishable configuration. So such flips that we're talking about are what we call the operations or symmetry operations, and it's defined generally as a symmetry operation is an operation whether you rotate, reflection, we'll talk about it in another video, a combination of both, that upon its performance on any object it brings a new configuration which is indistinguishable. That means you cannot differentiate it from the original configuration. The symmetry elements present in molecule, they are the identity, the proper axis or rotational axis, the symmetry plane or reflection, the inversion center or center of symmetry, and improper axis. So, or improper rotation, and these are their symbols. Identity is E, rotation, that's through a proper axis, is Cn, reflection through a symmetry plane is given sigma, and then inversion, that's the through a certain point. So we have rotation about an axis, inversion about a point, it's given symbol I. And then there's improper rotation, which is a combination of rotation and reflection, and it's given the symbol Sn. So let's look at the identity operation. The identity operation is given the symbol E. It's from the German language. Anyway, it means that you do nothing on the molecule. So the molecule retains as it is. Every molecule possesses this operation, because if you don't change any molecule, it still looks the way it is. So it's do nothing. It's called identity operation. It's the only symmetry operation that even some molecules or even most molecules have. However, okay, so why are we considering it? The reason we consider it is because it is useful in good group theory. So that's the number one, and that's do nothing, identity. It's called the identity operation. So let's look at the rotation. That's a little bit more tricky than the identity. So the rotation is also called the proper rotation or n-fold rotation. So it's rotation about an axis through the center of mass by an angle. Rotate it at a certain angle theta, where theta can go from 0 to 360. 360 in radians is 2 pi. So it can, and n has to be an integer, so it's 360 over theta. So whatever gives n an integer, and you can rotate the molecule in that direction. So the rotation is done along a line known as axis of rotation. If we look at this square, if there's an axis perpendicular to this plane that we're looking at, but at the center of the molecule, and you rotate it through 90 degrees, such that A comes to this place as in this figure. So you rotate it by 90 degrees. We see that the shape is exactly the same as before. It hasn't turned into like a diamond or a kite or a rhombus. It still has the, at least from our point of view here, so it still has the shape of the initial pattern. So that's why we say it's indistinguishable. So to distinguish it, if we're just to draw it just out there, we really wouldn't distinguish it. So we had to label A so that we know we are doing the rotation. So this rotation is a 90 degrees rotation. You can also go from here through another 90 degrees rotation, and then you can take it back a 90 degrees rotation, and then you have a fourth time rotation to get back to the, so they all look alike. So that's the thing about symmetry. On the other hand, so the rotation is about 90 degrees to get an indistinguishable configuration. So our n is 360 over 90, and that's equal to 4. So that means that's the axis that passes through the center of molecule and perpendicular to the square is a C4 rotation axis. The square, the rectangle, if you give it a 90 degrees rotation, but the layout that we can see is different from this layout. So if you were, again, if you're using the idea of the lock and key, if we were trying to put this take this as your key and lock it, once you rotate it this 90 degrees, it doesn't fit where this is. So this is distinguishable. However, if you do another one, that's the 180. So that's 90 plus 90, that's 180. We see that we have our indistinguishable shape. So a 270 doesn't give us that, but another 90. So this rectangle rotation about the 90 degrees yields a different configuration. So it does not have a C4 rotation axis. However, a rotation about 180 degrees yields an indistinguishable configuration. So it therefore has a it has a C2 rotation axis and not a C4 rotation axis. We look at it again. Before we leave this place. So this is C4 1 time, C4 2 times, this is C4 3 times, and this is C4 4 times. So we write that as C4 raised to power 4. We'll look at it in a minute. So if we look at some other considerations, if you flip this square along an axis that bisects these two lines, so such that this now comes down here, so we have, that's a 180 degrees rotation. So 360 divided by 180 is 2, so we have a C2. Similarly, along this line, like we saw in the first slide, and we arrive at this, you have another C2. The rectangle also has this flipping over, which is a 180 degrees rotation. So we have C2 here and another C2 axis here. The triangle, a rotation for this one is a rotation through an angle of 120, so that we have 360 divided by 120. So that's a C3 rotation axis that is perpendicular to the flat surface of the triangle and passes through the center of a axis. So now let's look at it with molecules. Water has a bent shape from our VACPR theory. So if we, just like we flipped over the rectangle just now, a rotation about an axis that bisects the, so let's look at it. So a rotation and about this that bisects this angle flips this hydrogen 1 here and hydrogen 2 here. So this is an indistinguishable configuration. So it's true 180 degrees. Our n is 360 over 180 degrees. So water has a C2 axis about a C2 rotation axis about this line. You can do it a second time and then we arrive at that. So this is what we're going. So this is C2 once to get here, C2 twice to get there. So we have it, it's written as C2 twice, C2 two times, C2 raised to power 2. So the thing is, if we look at this configuration A and configuration C, well, we realize that they are the same thing. So if you rotate, if you perform the rotation C2 two times, you get to the identical shape before originally. So we say it's identical to the identity element. So a C, so generally it's so subsequent C2 rotation returns the molecules to its original geometry. It is represented as C2 twice. To the subscript indicates the axis of rotation, and the superscript indicates the rotation was carried out a second time. So we see that the C22 is equivalent to the identity operator, and generally the operation CNM implies that a rotation through an angle theta be carried out m times, and when our m equals to n, then the operation, which is now CNM, is equivalent to the identity operator. Let's look at another example of rotation in a molecule. So this is ammonia. Ammonia has a pyramidal structure, so it's like a triangle, but the nitrogen is sticking out of the triangle like in a triangular based pyramid. But we can consider the 3 hydrogen atoms in an equilateral, at the corner of an equilateral triangle with nitrogen at the center sticking out. So so this is our nitrate ammonia, and we can also draw it in such a way that we see the lateral view. So a rotation, C3 rotation in this direction brings H1 here and H2 out. So we have C3 one time getting us from A to B, so it exchanges H1 to this side, H2 comes here and H3 goes there. So we can do it twice, and from there we go from B to C. And then again, if we do it a third time, we arrive at D, and D is identical to A. So C33 equals identity. So the molecule has a C3 axis of rotation because we rotate it by 120 degrees to get to the original, to an indistinguishable configuration. A linear molecule, you just keep rotating it and you still have the same thing. So we say it has infinite axis of rotation, and it's labeled C infinity. So the last one that we want to consider is a PTH4 molecule. This is a flat molecule. PT is at the center. It's a rectangular shape, square shape, and the hydrogen atoms are considered to be at the edges. So the 4 atoms that lie at the edges are the corners of the square. A 90 degrees rotation, so we have already done the square the other time. So a 90 degrees rotation takes A to B, which is indistinguishable. So a second rotation takes B to C, and a third rotation takes C to D, and a fourth takes D to E, which is identical to A. So again, CNN is equal to E. So the molecule has a C4 rotation axis. So a second one goes to C, third one goes to D, and that one goes to A. In addition, so in general, for a multiple rotation, if we look at C4 two times, that's already 180. So a C4 rotation is equivalent to a C2. So in general, if you have Cn m times, if n over m is an integer, then CNM is equal to CW. Like here, 4/2 is